Okay, we're looking at parametric equations in this video. Now, the way these work is rather than having an equation like y equals stuff in terms of x, we're specifying both x and y in terms of another parameter t. So, for example, we've got this person lost at sea and they're floating according to this position data, and we need to figure out where they are. So, at time equals 0 hours, what you'd want to do is you'd want to plug t equals 0 into this. So, you'd get 2 lots of 0 take 3 and 0 squared take 2. If you simplify that down, you get minus 3 and minus 2 for the position. Next one here, you're going to get 2 times 1 take 3 and 1 squared take 2. So if we figure out what that is, so that's going to be minus 1 for the position there. And for the y position, it's 1 squared take 2, so that's also minus 1. For your next one, if we just keep plugging it in, so you're going to have 2 times 2 take 3 and 2 squared take 2. So that's going to be 1 and 2. The next one is going to be 2 times 3 take 3 and 3 squared take 2. So that's going to be 6 take 3, so that's 3. And then the y value is going to be 9 take 2, so that's 7. And for your fourth one, so that's 2 times 4 take 3, and it's 4 squared take 2. So this is going to be, let's see, 8 take 3 would be 5, and then we've got 16 take 2, so that's 14. Now the x values are going up by 2 each time, so that's a pretty nice linear relationship, but the y values are like a quadratic, so they're moving a bit differently. Next we can graph their path, so we're just going to chuck sort of our usual scale on here, going up to 10 each way. We won't be able to fit that last point on there, but we should get the idea of what this looks like. So we got to put in this point at minus 3 and 2. So that would be minus 3, minus 2 would be down here. And then we got minus 1, minus 1. And then we've got 1, 2, 3, 7. And the last one, if we could fit it in, would be at 5, 14. So sort of would be up there-ish. We can sketch the path that this person takes. And we could even label it with the parametric equations themselves. So 2t take 3, and then t squared take 2. Okay. Now, you don't need to draw this on your graph, but I'm just going to label time equals 0, time equals 1, time equals 2, and time equals 3. Just like that there. Okay. Now, we absolutely can graph this with technology. So for example, if you just type in the brackets like so on Desmos, it does this, and you can set like a maximum t value. So if we set that to 2, you'll only get a little bit. If we set it to 10, you'll get quite a bit more, and it goes out pretty far, all the way up there. You can also graph these on a calculator. So if we do that, what you need to do is just do like a normal graph, as you would. But we're just going to clear out this stuff, and we're going to shift into parametric mode. So you just hit type, so that's F3, param for parametric, and then we can enter our equations. So the x button will now actually be t, 2t take 3, and t squared take 2. And if we draw that, we should probably set our window correctly. So let's go just standard for everything. And we'll look at that. You can also set your t value. So if you look further down on your window, you'll start having t's. So if we set it to like 1, for example, you'd see I'd only get a little bit of that. And let's just match what I've done on Desmos. So let's set t max to 10. If we look at that, then we get more of it at least. Next thing we really like to do is converting these to Cartesian form. So what have we got? 2t take 3 and t squared take 2 is our equation. And the way that we like to do this is to rearrange usually the simpler one. So x is 2t take 3. That'll be nice to rearrange. We're going to rearrange it for t. So x plus 3 is 2t. And so t would have to be x plus 3 all over 2, just like that. Okay. So now that we've got that, we can sort of sub it into y is t squared take 2. And t is supposed to be x plus 3 over 2. So y is going to be x plus 3 over 2 squared take 2. This will give you x plus 3 all squared over 4 take 2. And I guess we could expand that out if we want. This is technically valid how we've got it here, but just for completeness, x squared plus 6x plus 9 all over 4, take 2. And we can actually graph that as well and just see if that works. So y is x squared plus 9 all over 4, take 2. And you can see that purple line does match the red line, and we just get the whole thing. So what we do is we call this version the parametric version. And then this is the Cartesian version. You can simplify this down a little bit more, actually, by like combining the constant terms in at the end. Okay, so we got this lighthouse at 5, that should be 7, 5, apologies, on the graph, and it can see in a range each direction. So I've got that range changed to 6 there. So let's plot this lighthouse on our graph. So the lighthouse is supposed to be at 7, 5. So we might just do it there. So 7 on the x, 5 on the y. And it's supposed to be able to see in 6 kilometers each way. So that'll be the bottom dot of the lighthouse. You'll see in like a circle shape. 1, 2, 3, 4, 5, 6. So there's the left dot. And then our top dot would just be sort of up there. And we can sort of draw around where this lighthouse is going to be able to see. So it'll see in like this circle-y shape here. Imagine that was a perfect circle. Now, what's the equation of the lighthouse? So if we're at 7, 5 and we can see in 6 kilometers each direction, this will be x take 7 squared, y take 5 squared equals 6 squared, just like that. Okay, and we've plotted it on the graph above already. And if we go back to our Desmos one, there it is. So we just plotted it there with the little circle. Perfect. So that's what it looks like if we draw the picture like super accurately. Okay. Now, find the time and positions where the raft enters and exits the lighthouse's range. So what we'd really like is for the circle equation, so this is x take 7 squared, y take 5 squared, and 6 squared, to equal the raft equation. Now we've got the Cartesian equation, but we're actually going to use the parametric version. 2t take 3, and y is t squared take 2. Now, really importantly, that is x and that is y, even as functions of t, you could think of them. So what we're going to do is we're going to sub the raft equation into the circle. So raft into circle. So where x was, we're going to replace with what that whole function was. So this was 2t take 3, take 7 squared. And with the y equation, we'll sub that in. So we've got t squared take 2 is the y value, take 5, and we're going to square that. So this should equal 6 squared. And now we can just go and solve for t. So we're going to get 2t take 10 all squared, t squared take 7 all squared equals 6 squared. And if we solve this, so this should be 4t squared, so 40t in the middle, plus 100, plus this will be t to the 4, 2 lots of t squared and 7, so that's 14t squared. And then that'll be plus 49 equals 36. We can start grouping some terms. So I'm going to have a 149 term on the end for my constants. I'm going to have t to the 4 on its own, and 4t squared and minus 14t squared. So that would be minus 10t squared. And then we just got a minus 40t term, plus 149 equals 36. So that's expanded and simplified fully. And let's see, so we're going to go t to the 4, take 10t squared, take 40t. We better take 36 from both sides. So that would be 113 equals 0. Okay, now depending exactly how this problem works out, this equation could be easy or hard to solve. In no way do I expect you to solve a quartic by hand. I would be very impressed if you could. But we just want to go into equation mode, polynomial solver, and we're going to go for a degree 4. We've got a quartic 0t cubed minus 10t squared minus 40t and 113 for the constant term. solve this lovely quartic, and we get two real solutions at least, 3.49 and 2.20. So we'll just make note of that. Groovy. All right, so we've got our times, and we'd like to know the positions. Now, to get the positions, we can just sub the times back into the raft equation. So what we can do is actually, I'm going to give you some quicker notation for this. So x of t and y of t is a function. We tend to call this grouped together vector the vector x. Now, it's really confusing because there's two x's here. The vector x is both the x and the y coordinates. It's a bit weird. But the reason we got that notation is because now we can talk about x at the time 3.49, and that'll be the actual just position coordinates for both things. So remember, this was 2t take 3 and t squared take 2. So maybe 2 lots of 3.49 take 3 and 3.49 squared take 2. And we can figure out what that is. Now, conveniently, if I go onto the calculator and we just look at graph, trace still works with parametric graphs. So if I go trace and type in 3.49, that'll give me a t value, like a position thing. I might just need to make my window a bit bigger. So let's make y go up to 20, just so I can see it. We draw that. Again, we're just going to go 3.49. It looks like 3.98 and 10.18. So I might just write that in right away. 3.98, 10.18, just like that there. And then the position at 2.20 we can get as well. So if I go trace at 2.20, 1.4 and 2.84. You actually have to look at the point itself on the calculator. You can see it's got it labeled with the coordinates there, 2.84. So this is where it goes into the range, and this is where it goes out. So any time between that, it's inside the range. And let's interpret this in the context of the graph here. So 3.98 and 10.18 should be that exiting dot that I just found, which it is. And then we should have another dot where it's coming in, 1.4 and 2.84. So 1.4, 2.84. So that red dot is where it's coming in. Okay, last question here. So the lighthouse really would like to predict where the boat is and then rescue them when they're getting as close as possible. So we sort of got this whole range when they're in. And the lighthouse itself is at 7,5. So it's this blue dot here. We'd like to figure out when that red line is as close as possible to the blue one. Now, there are formal ways to do this. You can use like perpendiculars and stuff, but pretend that you just didn't know that. We could look at the distance from the raft to the lighthouse. Now, the raft equations here are 2t take 3 and t squared take 2. And the lighthouse equations are, well, it was at 7,5. Now, you can use the distance formula, but I'm going to call this R and L. Let's just look at the vector. Be really careful about how you do this. Lighthouse to raft. So this would be the coordinates of the raft bit. Take the coordinates of the lighthouse bit. And then if we smoosh those all together, that's 2t take 10 and t squared take 7. Cool. Okay, so that is lighthouse to raft as like a vector. Just be aware that a vector is going to be pointing in different directions depending what t is. So if you sort of got your lighthouse here, it might be pointing up there or whatever, depending on where the raft actually is at that time. And how do we find the distance? Well, we just got to go mod LR. Okay, so this would be root of 2t take 10 squared and t squared take 7 squared. Now, you can absolutely use calculus to deal with this. So what you could do is differentiate the distance function and then set it to 0. But let's just use technology to find this. So we're going to go out. We're not going to go parametric mode anymore, so I might just go back to y equals. It'll still keep the parametric equation in there, but I might actually get rid of those for now. And we're literally just going to graph our distance function. Okay, what's that? 2x take 10. And t squared take 7. All right, so we've just got this distance equation graph now. And let's hit enter and we'll have a look. So there's our distance function. It's a bit wacky, but we just got to go g solve min. So again, you could do this all with calculus, but I'm going to use technology here because if you use calculus, you'll probably need polysolve for a cubic or something anyway. So the way that we interpret the axes, first of all, is that this is time and this is the distance. And so the min distance is 4.43 kilometers when t roughly equals 2.91. Now, we should probably get where the raft actually is at that time as well. So it was 2t take 3 and t squared take 2. So if we have a look at what that becomes, we've got, just in normal calculator mode, 2 times 2.91 take 3 would be that value, so that's 2.82. And t squared take 2, so that's going to be 2.91 squared take 2, and we get 6.46. So in theory, if I graph that point, 2.82 and 6.46, let's see what that looks like. So you can see that green point there is apparently supposed to be the minimum distance. And I'm hoping you can sort of agree that if you're waiting for the raft to get really close to the lighthouse, it probably would be that green point where it's the closest.